Hello, AP students. This is going to be the first in a series of lectures about oscillations and then waves. We'll begin with simple harmonic motion as applied to masses on the springs and uniform circular motion. This is chapter 11 of the Giancoli textbook. I'm going to leave the screen in this split screen configuration where you'll be seeing the PowerPoint on the left and then examples and other notes on the right in real time. So, simple harmonic motion, section 1. We discussed this at the end of class on Wednesday, February 7th. But there was a lot of back chatter, and we should probably make sure everybody's on the same page. If and when an object vibrates or oscillates back and forth over the same path, each cycle taking the same amount of time, we call that kind of motion periodic. A mass on a horizontal frictionless surface attached to an ideal spring is a useful model for a periodic system, and it's one we can treat in detail. So our focus will be masses and springs. We'll then expand that focus to uniform circular motion of a particle. We'll then look at some pendulums of various types. And after all of that, we'll start applying our ideas of oscillations to mechanical waves. So when we're considering this horizontal mass and spring system, we are going to assume that the surface is frictionless. That will allow us to consider conservation of momentum, or rather, conservation of mechanical energy without any transformations of energy to heat. So, there is a point where the spring is neither stretched nor compressed. This is called the equilibrium position. We've already looked at springs enough that this should be a review. We're going to measure displacement from that point, the equilibrium position, which is determined to be x equals 0. As we already know, an ideal spring follows Hooke's law, and the force exerted by the spring depends on displacement. So Hooke's law, ideal springs, exert force according to the equation F equals negative kx. The k there, that lowercase k, is the spring constant, and that's a measure or an indication of how strong or weak the spring is. X is displacement from equilibrium, so how far to the right or left the spring is stretched or compressed. And the negative sign indicates that that force is always pointing back towards equilibrium position. So if you stretch the spring from equilibrium to the right in the positive x direction, the force is negative to the left. If you compress the spring to the left in a negative x direction, the force is positive and to the right. I've actually just said all of this. So the minus sign on that force equation indicates that it's a restoring force. I'm not sure if we've used that word before. A restoring force indicates that it's restoring the mass to the equilibrium position. Lowercase k is that spring constant again in SI units, newtons per meter. And it's very important to understand that a spring does not exert a constant force. So the acceleration produced by the spring is not constant. So we cannot apply the equations of motion, the kinematics equations for constant acceleration, to the motion of a mass attached to a spring. Let's talk about some vocabulary. Some of this is review. So again, displacement, which we term x, is measured from that equilibrium position. We use a sign to indicate direction, positive to the right and negative to the left. Amplitude, capital A, is, I think, new to us. Amplitude is the maximum displacement the block spring system undergoes. So amplitude is as far as it goes to the right or as far as it goes to the left. It's positive or negative. One cycle is a full to and fro motion. So if we're stretching the spring to the right to position A, x equals A, and letting it go, one complete cycle is the block moving to the left and then coming all the way back to x equals positive A again. The period, again using capital T as sort of important time measurement, is the time it takes to complete one cycle. We've referred to period in terms of circular motion. We'll now focus on this horizontal but repetitive motion. So period still applies. And then frequency is the number of cycles that are completed per second. I think that grammar's messed up, but period and frequency are inverse of each other, and are one is sometimes more useful than the other, but once you know one, you know the other. Okay, so an example question. We have a mass on a spring in simple harmonic motion, which we still haven't quite defined. It has amplitude A and period T. What is the total distance traveled by the mass after one period? Think about this for a moment. So after one full period, the mass has gone from, let's say, its stretched position at plus A to 0, so that's 1A. Then 0 to negative A, that's another A. Negative A back to 0, there's another A. 0 back to positive A. So 4 times the amplitude. There's another conceptual question. A mass on a spring in simple harmonic motion has amplitude A and period T. What is the net displacement of that mass after time interval T? So after one complete period. So the difference here is, first we asked total distance traveled. Now I'm asking, what's the net displacement? The nature of harmonic motion, the nature of periodic motion, is that the object continually returns to its starting position. So net displacement is ending position minus starting position, x2 minus x1. And since this object, by definition, returns to its original position after one complete period, the net displacement is 0. A mass on a spring in simple harmonic motion has amplitude A and period T. At what point in the motion is the velocity equal to 0 and the acceleration equal to 0 simultaneously? So to answer this question, you need to think about Hooke's law and how the force the spring exerts on the block depends on how far the spring has been pulled. And of course, acceleration is directly proportional to force, according to Newton's second law. And then you need to think about where in its motion is the object moving the fastest, and where is it at a turning point? So the correct answer is none of the above. The acceleration is 0 when the spring is in equilibrium position, so at x equals 0. But when the spring is in equilibrium position, the mass is going as fast as it ever goes. It's moving through that position where there's no force. As the spring moves further through its oscillation to the left or to the right, the spring starts pushing or pulling with larger and larger force, causing the mass to slow, eventually to a stop at its turning points, negative A and positive A. When it reaches the turning point, it's momentarily stopped, velocity equals 0, and at that point, the spring is maximally compressed or stretched. So at that point where velocity equals 0, the acceleration is at a maximum. Acceleration and velocity are sort of offset from each other. Okay, so we will look at masses on springs that move horizontally with no friction, and we'll also consider masses on springs that are hung vertically. If the spring is hung vertically, the only change in its motion is the equilibrium position. Instead of equilibrium position being the horizontal equilibrium position, the new equilibrium position accounts for the fact that the spring has to provide equilibrium for the mass when it's at rest. So the spring stretches until the spring's force up equals the mass's weight down. From there, the oscillation of the spring and mass proceeds exactly as it does if it's a horizontal mass spring system. So in general, any vibrating system where the restoring force is proportional to the negative of the displacement is in simple harmonic motion and is often called a simple harmonic oscillator. So the thing is, if you can find a way to show that the force, whatever that force may be, driving a periodic motion looks like Hooke's law if it has a form like F equals negative kx, or maybe F equals negative constant times x, and maybe that's y, maybe that's r, but as long as force is proportional to position, but restoring, so backwards, opposite to the direction of stretch or direction of motion, then we consider this to be simple harmonic motion, SHM for short. That's the definition of simple harmonic motion. So we want to consider the energy involved in simple harmonic motion. We already know a lot about mechanical energy, and we know about how springs can hold mechanical energy. We know that the potential energy of a spring is given by half times k times x squared. That came from looking at the work done in stretching or compressing a spring and finding the area under the force versus distance graph. The total mechanical energy of a mass spring system, then, we're thinking about this mass m and spring with constant k, anywhere in its cycle needs to be the combination of kinetic energy, is it moving, and if it's moving, how fast is it moving, plus spring potential energy. Whoops, I meant to write U sub S. So we have this combination. Mechanical energy is it moving? If so, how fast? And then is the spring stretched or compressed? If so, by how much? At any moment in time, it could be a mix of either of these energies, or it could be one or the other if it's at an endpoint or at equilibrium. This is only for a horizontal system. If we're considering a vertical system, then we have to add in gravitational potential energy. We're assuming that the system is frictionless again, so no friction here, so that we don't have to add a term for the work done by friction. So if the mass is at one of the limits of motion, so if the mass is at the place where the spring is maximally compressed, or at the place where the spring is maximally stretched, and here's equilibrium, then the mass is momentarily at rest. V equals 0, V equals 0. But the spring is at compression or expansion of amplitude A. So all of the energy held at these points is spring potential, because the spring is as stretched or compressed as it ever gets, and the mass is momentarily not moving, so there's no kinetic energy. When the spring is at equilibrium position, so as the spring passes through x equals 0, there's no spring potential energy because x equals 0. The spring is at its equilibrium position, and the mass in turn then is moving as fast as it ever moves. So we'll at least begin our evaluation of energy in simple harmonic motion by focusing on those limits, those turning points and the equilibrium position. So we can relate the total energy at the turning points to the total energy at equilibrium. We can say the total energy at the turning points is half kx squared, and the total energy at equilibrium, I should probably label it as k, is half mass times speed squared. And of course, at the turning point, the value of x is the amplitude plus or minus, but we're squaring that value, so whether it's on the left side or the right side doesn't matter. That must be equal to half times mass times the velocity at the equilibrium position, which is the max velocity, quantity squared. So I can now solve for that maximum velocity compared to amplitude, or amplitude compared to maximum velocity. There's a half on both sides, that factors out. I can take the square root of both sides since I have a squared and v max squared, or I can solve for v max squared first, however you like to do it. V max squared is k over m times a squared. And of course, v max then is equal to plus or minus, right? It's either going to the right or to the left. Square root of quantity k over m times amplitude. It's kind of interesting that maximum velocity depends on spring constant. So how strong is that spring? How strong is it pulling on that block every displacement, divided by how much mass is resisting the pull, multiplied by how far did you sort of disturb the mass from its equilibrium position. We can also relate the total energy at the turning points to the total energy at any point in the oscillation. So in general, we have total energy equal to kinetic plus spring potential, that is half mass times velocity at some particular point plus half k times that position at that particular point, not the maximum velocity and not the amplitude, but some combination in between. But we know that this total energy always has to be equal to either half ka squared or equal to half mv max squared. Oops, I ran off the page, ran off the screen. So we have total energy any point, total energy at turning point, total energy at equilibrium. And the law of conservation of energy says that if there's no energy transformed into heat because of the work done by friction, these three quantities need to be equal to each other. So I can relate that total energy at the turning points to the total energy at any point in the oscillation. I think I'll go ahead for time's sake and skip the derivation, but once I've related my equation for total energy at any point to the energy held at the end point and then substituted for maximum velocity, I'll end up with a velocity at any point in the cycle equal to plus or minus, because it could be going to the right or to the left, and that to the right or to the leftness is symmetric about the equilibrium position, v max times the square root of 1 minus x squared over a squared. So we have velocity at any point equal to the sort of limit is either maximum to the right or maximum to the left, which occurs at x equals a, but it's less than that whenever x is anything less than a. This is a very useful equation for finding the velocity at any point in the oscillation cycle. Okay, so let's try the concept at least. A mass oscillates in simple harmonic motion with amplitude A. If the mass is doubled but the amplitude is not changed, what will happen to the total energy of the system? So we can refer to our equation here for total energy, right? We're not really going to talk about energy at some random point, but we could look at the equation for energy at the maximum compression point or energy at the equilibrium point. Does that equation help you answer the question? The answer is that energy does not change. If we double the mass, that necessarily means that the maximum velocity will be different. However, doubling the mass doesn't change the fact that total energy also has to be equal to half times spring constant times amplitude squared. If the amplitude of a simple harmonic oscillator is doubled, which of the following quantities will change the most? This is a bit of a trick question because we haven't talked about how frequency or period depends on the amplitude, but you might as well make a guess. It turns out that doubling the amplitude, so doubling this value, since velocity is also squared, does change velocity, but doesn't change it as much as doubling amplitude changes the total energy. Because amplitude is squared, total energy depends on amplitude squared, and you quadruple total energy when you double the amplitude. If you double amplitude, you only double velocity, or maximum velocity, I should say. So now we'll do a computational example. A fisherman's scale stretches 3.6 centimeters when a 2.4 kilogram fish hangs from it. What's the spring stiffness constant? So that's the spring constant K. And what will be the amplitude and frequency of oscillation if the fish is pulled down 2.1 centimeters more and released so that it oscillates up and down? Oh, you know something? I think we have to come back to this. I've put this in a bad order because we really haven't looked at frequency and amplitude yet. Let's come back. or rather frequency. Amplitude is how far it's stretched from equilibrium. But to talk about frequency or period, we need a little more information. So this is my mistake. We'll come back to slide 21 after we've discussed frequency and period. And in order to discuss frequency and period, I want to compare oscillatory motion with the mass on a spring to simple harmonic, or rather uniform circular motion, and that will allow us to develop a relationship between period and frequency and those things that may or may not affect the motion of a mass on a spring, namely amplitude, mass, spring constant, etc. So making a note to myself to return to slide 21. Okay, so if we pull a mass, a vertically suspended mass, away from equilibrium and sort of allow that mass to trace out a graph as paper moves past it, the paper moving past it at a constant rate, we'll develop a graph of mass's position versus time. If we do so, and in fact we may do so in the lab using a motion detector, we'll find that the path of this up and down motion, when we spread it out over time, looks like a sinusoidal curve, so sine or cosine function. If we've displaced the mass from equilibrium either up or down and released from rest, the shape will be either a plus cosine something times time, or a minus cosine of something times time. So the equation x equals a times cosine of ct. A is the amplitude, either above or below equilibrium. That constant c allows us to sort of fit the period of oscillation to the actual period of motion, right? It allows us to scale the time appropriately. And that will be how we determine the frequency and period of our oscillation. So it turns out, if we look at the projection onto the x-axis of an object moving in a circle of radius a at constant speed v max, we find that the position of the object varies with time. So this is looking at a view from above in the top picture of what's actually happening. But what we're plotting is not the view from above, we're plotting the view from the side. So if we look straight on to this circular motion from the side, we don't see the particle moving in a circle. Instead, we see the particle appear to move to the left in a straight line and then stop and turn and move to the right in a straight line. And it turns out, because the position is equal to amplitude A, amplitude isn't amplitude anymore, but it's actually the radius of the circle. So the position is mapped onto the x-axis is equal to the radius of the circle, which we're now calling A, times cosine of theta. We're looking at the x component of that circular motion. It's weird, but it turns out to be a cosine function. Then furthermore, we know that the angular position, that theta position, right, we're looking at the circle and the radius A, this position theta varies with time. We already know how angular position varies according to angular velocity. Theta has to be equal to velocity times time because this velocity is constant. So I can substitute then. Position is equal to A times cosine of theta, but now theta I can express as omega t. And now I have a term that corresponds to my C. So when I mapped the oscillatory motion of a mass on a vertical spring, I had a constant in front of the cosine function that had to do with amplitude. Here's my amplitude. And then I had a cosine function that had to vary with time, but it had to be scalable to the period. I now have that for circular motion. So the form of the position equation is the same for circular motion as it is for a mass on a spring. It is simple harmonic motion. Another way to define simple harmonic motion, so our first definition is that simple harmonic motion must be driven by a Hooke's law form restoring force. Another way to define simple harmonic motion is motion whose position is a sinusoidal function with respect to time. And we have that here. So if I look back on the diagram of circular motion as seen from above, the relationship between x and a, so this relationship between the x component that I'm viewing here, the x component of motion, and the radius of the circle, is similar to the relationship between the maximum velocity, so that's the tangential velocity, and the x component of that velocity. You form a set of similar triangles, you look at the ratio between moment to moment x component velocity, so on the PowerPoint slide that's v, versus the maximum velocity, and that's a similar triangle to the hypotenuse of the height of the triangle formed by a and x, so square root of a squared minus x squared, using the Pythagorean theorem, over the hypotenuse a. And that allows us to solve for the moment-to-moment velocity. Solving for the moment-to-moment velocity, we get the equation velocity equals v max times the square root. I'm going to write it down because I'm going to go back to the previous slide. V max times the square root of 1 minus x squared over a squared. And that is significant because when we evaluated energy, we came up with the relationship v equals plus or minus v max 1 minus the square root of x squared over a squared as well. So everything matches. The the simple harmonic motion of mass on a spring, mathematically or equation-wise, matches the mapping of uniform circular motion in one dimension. So we've mapped uniform circular motion onto simple harmonic motion, and we understand uniform circular motion pretty well. So we're using that to help us understand simple harmonic motion. When we were talking about uniform circular motion, we talked about how that constant tangential velocity, v, has to be equal to the total distance the particle travels around its circular path per time it takes to travel that circular path. So distance around a circle, circumference of a circle, is 2 pi r, and the time it takes to complete one complete circle is defined as the period. So we can write that tangential velocity as 2 pi times a, because we've defined the radius of this circular path as amplitude capital A, and then divided by period. So now we have a way to relate that maximum velocity to the amplitude in period. So we're saying, because we know about circular motion, v max, the tangential velocity in circular motion, is equal to 2 pi a over t for our uniform circular motion. When we were talking about energy conservation and simple harmonic motion of a mass on a spring, we said v max was equal to the square root of k over m times a. And so by comparison, or rather, we can solve this equation for period, right? We have now a relationship between amplitude and spring constant and mass. We can solve this equation here for period and say that period is equal to 2 pi times the square root of mass over spring constant. And so finally, from combining our understanding of conservation of energy and combining our understanding of uniform circular motion, we now can talk about how the period, so the timiness of those oscillations of mass on a spring, relates to the stuff we know about the spring, so the mass connected to the spring and to the spring constant. And kind of surprisingly, amplitude isn't a factor for period or frequency. Amplitude in our v max equation was on both sides of the equation, and it factored out. So period is 2 pi times square root of mass over k. If I have a larger mass hanging from my spring, I should expect the oscillation to take longer. If I have a stronger spring, I should expect the oscillation to take less time. It's snappier. And we can kind of confirm that in an experiment. Frequency, of course, is the inverse of period, 1 over period. So we can just say that frequency now is 1 over 2 pi times the square root of k over m. We're just inverting the entire thing. So again, remembering that period is the time for one cycle. Frequency is the number of cycles per second. So we can say that the position function that we had developed previously, so x of t is equal to a times cosine of omega t, we remember that frequency is number of cycles per second, and that angular frequency is radians per second. And we can switch from frequency in hertz to angular frequency in radians per second by saying that one cycle is equal to 2 pi radians. So if I'm saying frequency cycle per second and I want to switch it to angular frequency, I need to multiply by 2 pi radians per cycle, and that allows me to convert from frequency to angular frequency. So angular frequency omega is equal to 2 pi times frequency in hertz. I'm not quite sure what to call this, just frequency. But that allows us then, I need another page here, to switch our position equation, so x of t is equal to a cosine of omega t. That's fine if we know omega, but we just developed an equation for frequency and period. We can also express it now as x of t equals a cosine of 2 pi frequency times time, right? So this is angular frequency if you know it in radians per second. This is frequency that we just derived, frequency being equal to 1 over 2 pi square root of k over m. And then similarly, of course, we can substitute period for frequency. X of t is equal to a times cosine 2 pi t divided by period. I didn't give myself enough room there, where if we like, we can say period is 2 pi square root of m over k. It's a lot to keep track of. I would suggest trying to memorize maybe the period equation and then just keeping in the back of your mind that frequency is the inverse of period. All three of these equations are telling us the same thing. So let's imagine a glider with a spring attached to each end. It oscillates with a certain period. Presumably this is horizontal, and being a glider, it will be low friction or no friction. If the mass of the glider is doubled, what will happen to its period? So if I put more mass on the glider, will the time it takes the glider to oscillate change? If it changes, will it increase or decrease? According to our equation for period, increasing the mass causes the period to be increased. I like that follow-up question below. What happens if the amplitude is doubled? So if you pull the glider back further, or if you give it a bigger push, what will happen? And again, surprisingly, nothing. The period will be the same. A mass is suspended from the ceiling of an elevator by a spring. When the elevator is at rest, the period is t. What happens to the period when the elevator is moving upward at constant speed? You will conclude that nothing happens to the period. With the elevator moving at constant speed, the equilibrium elongation, that means that extra little stretch of the spring is the same, and the period of the simple harmonic motion is the same. What about if a mass is suspended from the ceiling of an elevator by a spring and the elevator is accelerating upward? What will happen to the period in that case? Unsurprising, the period will not change. So when the elevator accelerates upward, the hanging mass feels heavier and the spring stretches a bit more to account for that. So the equilibrium elongation of the spring, that equilibrium position, will increase. However, and surprisingly, the period of simple harmonic motion does not depend on the elongation of the spring. It only depends on the mass and the spring constant, and neither of those things have changed. So this would be sort of like taking your mass spring system to a planet where the pull of gravity is heavier, harder, larger, whatever. Again, the mass and spring would oscillate at the same rate on that planet with a larger pull of gravity as it does here on Earth. And on the other extreme, a mass spring system will oscillate at the same rate if you take the mass spring system into outer space where there's no gravity or microgravity. The oscillation does not depend on the pull of gravity. It only depends on the strength of the spring and the amount of mass attached. So switching from displacement to velocity to acceleration, or at least proving the switch, really requires us to delve into calculus level mathematics. So you're going to have to accept my statement, my affirmation, that if we plot displacement, if we express displacement as x of t equals a cosine of omega t, then it turns out that the velocity function is equal to a different constant. I'm going to call it d times sine of omega t with a negative sign in front. The sine function is flipped upside down. And that d, that a different constant, is equal to omega a, which we now recognize as v max. So that makes sense, right? The velocity oscillates also in a sinusoidal sense with the same period, right? The period didn't change. The velocity changes at the same rate that the position changed because it all has to fit into that same oscillatory motion. The velocity swings between positive and negative maximum velocity, and when the sine function is zero, the velocity is zero. So it kind of makes sense conceptually, but to prove this relationship requires calculus. Calculus friends, you can take the derivative of the position function and prove the velocity function. And then additionally, the acceleration function. Oh, actually, we don't need calculus to prove this now that we can say that acceleration is force over mass. And we know that force, the force driving this is Hooke's law, so kx over mass, negative kx over mass. And we have an equation for that position function. So we substitute a is equal to negative k over m times the position function, which is a cosine of omega t, where I should really be calling it like 2 pi square root of k over m or whatever t, right? So in any case, we end up with this new constant in front and a negative of a cosine function. This term in front, k over m times a, turns out to be the min and max acceleration. Again, calculus friends, you can derive this equation by taking the derivative of velocity with respect to time. Ooh, look at that. That is awfully fuzzy. Okay, but let's go back now to slide 21 and see if we can make sense of that question. So the question on slide 21 was, a fisherman's scale stretches 3.6 centimeters when a 2.4 kilogram fish hangs from it. So what's the spring stiffness constant? What's K? And then what's the amplitude and frequency of oscillation if the fish is pulled down 2.1 centimeters more and released? So I'm thinking spring scale, that's a spring, and I'm attaching a fish to it. The fish is a box, and my document cam needs to refocus. It's supposed to be on autofocus, but I think my hand confuses it. Okay, so we have a spring and a mass, and the mass is a fish. And we have a 2.4 kilogram fish, and when I added that fish, the spring stretched a distance of 3.6 centimeters from its equilibrium position. So that tells me that in this equilibrium position, where I have pull of gravity Fg down on this fish and spring force up on the fish, and these two must be in balance because it's equilibrium, that spring force equals Kx equals mg. And that tells me that the spring constant needs to be equal to the mass, so 2.4 kilograms times acceleration due to gravity, 9.8 meters per second squared, divided by the stretch from equilibrium. So 3.6 centimeters, but I need to be in meters, so 0.36 meters. So my spring constant then, you can experience my real-time calculation here, 2.4 by 9.8 divided by 0.036. So I've got 653.3 repeated, 653 newtons per meter with our sort of rule of thumb of 3 sig figs is fine. Actually, we should have 2 sig figs, right, given the numbers in this problem, but we don't really care. So spring stiffness constant is 653 newtons per meter. What will be the amplitude and frequency of the oscillation if the fish is pulled down? So from this position, I grab the fish with my hand and pull further down a distance of 2.1 centimeters and then release. Okay, well, I think about that graph, right? I have the spring, I have the mass on the spring, and at t equals 0, this is time, right? And this is x, or this is actually y now. I pull it down to its maximum position. It then comes back to equilibrium, x equals 0, and then rebounds sort of above equilibrium, and then comes back to equilibrium and back to its starting place. That's the oscillation, right? So this pulled down position of 2.1 centimeters is the amplitude of this sinusoidal oscillation. This is actually negative 2.1, and then of course this is positive 2.1. So the amplitude is easy. That's 0.021 meters, or 2.1 centimeters. What is the frequency of the oscillation? For frequency, of course, we need to go back to our frequency equation, our derived frequency equation, and that was 1 over 2 pi square root of k over m, so number of oscillations per second. So frequency, 1 over 2 pi square root of k over m. So 1 over 2 pi square root of k, which we've determined to be 653 newtons per meter, divided by mass of 2.4 kilograms. That's the mass of the thing attached to the spring. 653 by 2.4 square root multiplied by 2 pi. I'm actually not sure where pi is. Oh, there it is on my calculator. So I get 103.67. That seems like quite a large frequency. 103 oscillations per second. I think, oh shoot, yes, I messed this calculation up. I multiplied by 2 pi. Okay, let's try that again. Maybe you should be checking my work and you can see my calculator here with some serious glare from the overhead lights. But 653 divided by 2.4, and then I take the square root of that. Okay, so 16.49. That's this term right here. But I need to divide by 2 pi, not multiply by 2 pi. 2 pi. Where did pi go? There it is. Right? So that's a much more reasonable answer. The frequency is 2.625, so 2.63 oscillations per second. But I was really concerned about a fish oscillating on a spring 100 times a second. I'm kind of accepting a value of about 3 oscillations per second. That seems more reasonable for a fish. Still, I'm wondering why you're trying to oscillate a fish on a spring, but you know, that's just me wondering why. All right, so let's try that additional problem. I'm going to get back to here. Oh gosh, I don't really know why that's so fuzzy, but we'll live with it. So we have a vertical spring with spring stiffness constant 305 newtons per meter, oscillating with an amplitude of 28 centimeters when 0.235 kilograms hangs from it. So that's telling us a whole lot, right? We already have amplitude, we already have spring constant. We have the mass of the object hanging from it. The mass passes through equilibrium with positive velocity at t equals 0. What equation describes this motion as a function of time? And at what times will the spring be longest and shortest? So now we're trying to think about mapping the motion of this object attached to a spring onto that sinusoidal function. So I'm thinking, when I pulled the spring away from equilibrium, or pushed it away from equilibrium, the previous one we pulled down from, right, we ended up with a cosine function that looks like this. And the displacement was negative a and positive a. And the period is the time from position back to position. So this time frame here is 1 period t. Okay, now we have a different scenario though. The mass passes through equilibrium at y equals 0 with positive velocity at t equals 0. So instead of a cosine function, I need to have my mass passing through equilibrium. So this is t, this is x. My position at t equals 0 needs to be here at equilibrium. And the mass is moving at positive velocity. So I need to be having slope up, positive slope, rather than slope down. So I'm here at t equals 0, and I'm about to go up. Okay? So what equation describes the motion as a function of time? So I know this is actually going to be not a cosine function, but a sine function instead. Let's read some more, right? The shape of the function starting at 0, x equals 0 at t equals 0, equilibrium at t equals 0 with positive velocity tells me that I should be doing this shape right here. So we've got the shape. Now let's try to fit the numbers to it. What's a and negative a? That's our first question. Well, the amplitude is 28.0 centimeters. So that answers that, 28.0 and negative 28.0. How would we describe this as a function of time? So we're remembering that x of t needs to have something about amplitude, cosine, but we're going to replace this with a sine, times omega t. So I now need to figure out what I put here for the angular frequency. So I need to know something about period and frequency before I can finish. This is fine. This is fine. We're actually going to replace with a sine function. We need to address the issue of timeliness. So I remember again that frequency equation. Frequency is equal to 1 over 2 pi times square root of k over m. And then I remember again that angular frequency back here when we were thinking just about units, 1 cycle is 2 pi radians. Angular frequency, the angular frequency is what shows up in the equation for cosine because we want to be unitless here. So angular frequency is 2 pi times frequency. So angular frequency, my omega, is equal to just square root of k over m. Right? I have 2 pi times 1 over 2 pi square root of k over m. So this will give me the timeliness of my sinusoidal function. The statement that it oscillates with amplitude of 28 tells me about how far it oscillates up and down. So my last little bit of info that I need to map this into a function is that omega is equal to the square root of k. The k value given to us is 305 newtons per meter divided by the mass, 0.235 kilograms. And so again, here, check my calculations. 305, oops, I turned it off. 305 divided by 0.235, and we take the square root of that. So I've got an omega of 36.025, I'm just going to call it 36 radians per second. Okay, so my final answer for part A then is what's the function? X of t equals A, amplitude. Let's be an SI unit, so 0.28 meters, times not cosine, because this isn't a cosine function, this is a sine function, of omega, 36 rad per second, times t. And now I have a powerful equation that tells me where this oscillating object is anytime in the future. And if I so felt like it, I could use the velocity and acceleration equations to know how fast it's going and how much it's accelerating. So here's my position equation. X equals 0.8 times sine of 36 radians per second times time. Now I go back to part B. At what time will the spring be longest and shortest? At what time will the spring be longest and shortest? So I want to know at what time is this position equal to the amplitude longest? And then, of course, shortest would be the negative amplitude. So I want to say x of t is equal to positive 0.28, and then x of t is equal to negative 0.28. And then I'm going to set this equal to my function and solve for time. I'm going to have to pause right now because fourth period is starting, so this will be a two-part video.